All right, so the next part of the conversion chapter is involving something called stoichiometry. Stoichiometry is just a fancy word for the ratio of atoms and molecules. So let me describe it in a little bit more detail. It's a quantitative relationship between starting materials and products in a chemical reaction. So for example, if we look at the first one here, one carbon atom plus one oxygen molecule makes one carbon dioxide molecule. That's why bouncing reactions is so important. You need to know the exact number of molecules required for an overall reaction to occur and the ratio of starting materials. So for example, right below it, it says if you have 1 mole of carbon atoms, that means you need 1 mole of oxygen molecules, and that will give you 1 mole of your final product. And you can convert that to number of atoms, which we know corresponds to Avogadro's number. And then below that, we can also correspond the moles to mass by using the atomic mass that we just practiced doing. In order to do any of this stuff, though, that you absolutely must start with a balanced equation. So let's start with an example, and we'll work through a few practice problems here. So in our first example, I'm going to take silicon dioxide and hydrofluoric acid. How many people have seen Breaking Bad in here? Yeah. So if you remember in Breaking Bad, they put hydrofluoric acid in a bathtub and it starts eating away. That's this reaction. Pretty gross. They make silicon tetrafluoride plus water. The reality is that show embellished a lot. I don't think it would eat through a bathtub like that. So now what we need to do, step 1, is always, always, always bounce this out to make sure that we have the correct equation shown. So let's check really quick. Give me a thumbs up if you think you got the bouncing done. Okay, so let's work through this just super quickly, guessing and checking. Right here I have 1 silicon on the left-hand side, 1 silicon on the right-hand side. Our silicons are bounced. Seems easy enough. All right, and then I would move over and I'd say, all right, I've got 2 oxygens right here, but I only have 1 oxygen on the right-hand side. Quick, simple fix to that, let's multiply water by 2. So now I've got 2 oxygens on the left-hand side, 2 oxygens on the right-hand side. We've bounced that. All right, so silicon's bounced, oxygen's bounced. Let's move over to hydrogen. Over here, I've got 1 hydrogen. Over here, how many do I have? 4, right? Because we've got 2 water molecules. Each water molecule has 2. So we've got 4. So we need to fix this, but that can be done pretty easily by multiplying this one by 4. That gives us 4 hydrogens over here. And last but not least, let's check our fluorines. So over here, I've got 4 fluorines. Over here, I've got 4 fluorines. Looks to me like this entire reaction is balanced. We need to balance it before we can do any of the math related to this chemical reaction. Does that make sense? In addition to that, sometimes students find it helpful if they even write in the 1s here. And you'll see why later on, but it's sometimes helpful to even see the 1s to imply that there's 1 mole of silicon dioxide for every 4 moles of hydrofluoric acid. Okay, so now let's try a few problems. Whoops. So the first one is going to be this. going to say, how many moles of HF do you need to make 3.66 moles of water? So let's try to work this out. Just like with any problem, always start out with what you know and just write that down immediately. So we'd say, all right, we know we've got to make 3.66 moles of water. It's the only value we're given. We know anytime you do a conversion, your goal is to cancel out your starting units. So I'm going to put moles of water on the bottom. And our desired unit, if we reread the question, is moles of HF, right? So I would put moles of HF on the top. And it looks like we've got a mole-to-mole ratio that we need to consider, right? How many moles of HF for every mole of water? And that's where we go back up and we look at that balanced chemical equation. So for example, I would go up here and I'd say, all right, I've got HF right here, I've got water right here. It looks like for every 4 moles of HF, you get 2 moles of water, right? So I'm going to pull those down for my ratio, and I'm going to say, all right, 4 moles of HF for every 2 moles of water. We can cancel out moles of water and get our moles of HF out as our final answer. So really, when we do this, it's like multiplying by 2. Give you 7.32 moles of HF. Had we not balanced our equation, we wouldn't have gotten the right answer, right? We needed to know that ratio before we could do any of this math. Does that make sense? All right, so let's try another one. Yeah.
Where did the multiply by 2 come from?
Oh, 4 over 2,
Okay.
right, is the same thing as multiplying by 2. I just kind of simplified it in my head. So if you can do it quickly in your head that way. If you're not super comfortable with that, just trust your calculator. That's fine. So let's do problem 2. Problem 2 is how many moles of silicon tetrafluoride are made when 7.89 moles of water are made. So sometimes these word problems trip people up, but like I said, simplify it. Just always start with what you know. The only value we know at this point is 7.89 moles of water. We know, just like before, we want to cancel out moles of water. So that needs to go on the bottom. And then this time what we're trying to solve for is moles of silicon tetrafluoride, right? So that's got to be the unit on top. And now what we need to do is we need to figure out the ratio of moles of silicon tetrafluoride to the moles of water. So we'll go back up. This time, we're not considering HF at all. We're just looking at this ratio of silicon tetrafluoride to water. So it looks like for every 1 mole of silicon tetrafluoride, you always get 2 moles of water for this specific reaction. So let's plug that in. So 1 mole of SiF4 is always in a ratio to 2 moles of water, right? So now, just like before, we can go ahead, cancel out moles of water, and we're left with the moles of the silicon tetrafluoride. So this time it's essentially like dividing by 2. So I'm getting 3.95 moles of silicon tetrafluoride. that make sense? So bouncing reactions can get tied into these unit conversions. I think we're going to stop right there today. Don't worry about the pod. If you want to try to get started on it over the weekend, go for it. More power to you. But we can work on it in class on Monday, and then you can turn it in at the end of class. So it'll be kind of like another small group practice activity. The carbonates lab will also work on in class a little bit. I really want to get good at stoichiometry, though, because it'll follow you into biology or your future chemistry classes.